Hello there and welcome to this course on Ensemble Learning with Python. My name is Valentine and I'll be instructor for the course. In this course, we're going to follow the following structure. So we'll get started learning more about the learning outcomes, which generally are the objectives that we need to work towards during the course. Once we have gone through that, we'll go to another section that will talk about what Ensemble Learning is, why we need to use Ensemble Learning, as well as when we need to use it. So during this section, we'll get to just discuss some of those Ensemble Learning techniques that will be important when it comes to working on any sort of data analysis or data science project that we might encounter. After that, we'll go through another section on reading and a quiz. So in this particular section, we'll go through a curated reading that we have provided, which you can see on your screen, that will go in depth with regards to the concepts that we will have discussed during the what, why, and when section of this particular course. So we'll give you this reading. You will need to go through it, which will just generally just be it will provide you with just in-depth details. And the idea is that once you have completed this reading within those 10 to 15 minutes, you'll need to work on a quiz, which will just help you to be able to check your understanding of the concept. So the idea here is that you're going to just go through this test as a way of evaluating to what extent you'll have actually understood those ensemble learning ensemble learning concepts. Once you have gone through that quiz, we'll come back then later, go through practice work. So putting into practice those theoretical concepts that we'll have learned. We've curated a practice notebook that contains different concepts with regards to ensemble learning. Whether there'll be practical concepts in relation to classification aspects of working with ensemble learning techniques, or whether there are going to be, whether it would be regression tasks that we will perform with ensemble learning techniques, that will also be covered in the practice aspect. That should take us about an hour or so and should give us a good, fair, and a good understanding of the concepts that we'll go through. You'll also notice that during this particular section, we have also provided some challenges that you can be able to work on by yourself, and you will be using the key lessons or key learnings from the examples that we have provided. Once you have done that, you can also um, verify the solutions that you'll have come up with for the challenges that we will have given you through the solution notebook that we'll have provided. Then once you have done that, we'll talk about a real life project that you can be able to use, that you will apply the ensemble learning concepts and techniques to provide a solution to. So this is a problem that will actually help you feel that you're ready to undertake other projects in relation to ensemble learning when it comes to your career. We have provided, in relation again to this project, we will have provided a guiding notebook that will be as a starting point for what you need to learn. The guiding notebook has already some curated details already there. So the idea is for you not so much to focus on the aspects of analysis that we haven't covered in this workshop, but to only generally focus on the data modeling or the machine learning aspect when it comes to applying the ensemble learning techniques. We'll have provided this notebook, and we'll also provide a solution notebook that will generally give you an idea of how to apply those different methods or the different techniques, ensemble learning techniques that you will have learned throughout the course. So there you have it. It's going to be a really compact learning experience, and we can't wait to um, go through this particular learning experience with you. Hopefully, by the end of it all, you'll be in a good position to just work on any sort of project that requires the application of ensemble learning techniques. So let's get started. So starting us off, learning outcomes. So by the end of today, we expected to have achieved these learning outcomes, be able to describe the concept of ensemble learning when it comes to making predictions, be able to differentiate between different ensemble learning methods, be able to um, use ensemble learning methods to create machine learning models. So using actually ensemble learning algorithms. And we should also be able to recall the limitations of using those different ensemble learning methods. So starting off, what is ensemble learning? Ensemble is just a learn. It's a French word that means together. Sometimes it may also come when you are thinking about an ensemble of maybe of musicians or people who play music. So an ensemble learning just means a collection, or an ensemble is just a many. So ensemble learning just generally is that process that we would undertake when we want to use multiple machine learning models in order to solve for classification or regression problems. Just to give us a good understanding of what the entire machine learning process entails. Um, when we're working with a machine learning model, we would normally be creating a machine learning model, which is a computer program generally that would make predictions. And in certain situations, we would want to make predictions for, say, variables, which is maybe a column of data within a data set, a tabular or a table. So we would have a column that we want to make predictions for. That column could be maybe customers. It could be customers would churn or not. So you could have a customer's data set that has a column called churn, and in that column you have yes or no, which would really mean that a customer churned, another customer did not churn, another customer churned. So yes or no would just correspond to those values for the respective um, customers that we have. So in a data set, we would normally have independent variables, which in data science, on data analysis, we would refer to them as features or predictor variables or input features. So in a data set that we would work with, which is tabular in a format, in a tabular format, we would have independent variables and a dependent variable. The independent variables are what we call features again, and the dependent variable, it's our target. It's what we are really interested in predicting, and that we would refer to that as a target variable, or we could refer to that as a label that we would want, or an outcome variable. So you might hear that we would be using them interchangeably, or you could even just learn about them somewhere else, that you find those words being used interchangeably, in some situations just one of those words. So when it comes to machine learning models, the idea is to use some historical data that contains independent and dependent variables, and we use that data to train a machine learning model to make predictions for any new sort of set of independent variables. So if a new customer comes with these sorts of characteristics, well, what would be the value of the dependent variable? So that's usually the entire process. But when we are starting out to create machine learning models, we normally work with what are called basic machine learning models. Or even just basic, which are usually based off algorithms. So algorithms are just complex mathematical functions that we can use to create machine learning models. And you could have quite a number of different algorithms. There's what is called a KNN, K nearest neighbor algorithm, decision trees. There's logistic regression, linear regression, different. Now, some other concept to also keep in mind is that when we also working on machine learning problems, we could decide to work on to create a machine learning model, or to train a machine learning model that predicts a target variable or dependent variable that is categorical in nature. So one where you would have, let's say, just some categories or classes, specific discrete categories in the variable of interest or in the dependent variable. It could be churn, could be a categorical variable with maybe yes or no. You could also have a categorical variable such as pass, or whether student pass with yes or no values. You could also have a categorical variable with um, um, uh, paid, categorical variable with that has values yes or no. So it depends. It depends. But if your variable of interest is categorical in nature, then we tend to work on classification problems, and we usually have just algorithms specifically for that. And on the other side, we could also have target or label, or which is also still the same, a different name of calling a target variable. A target variable that has numerical values. Maybe we want to predict the price of a house, or the height of someone, or some sort of numerical variable, numerical value. In such a situation, we tend to refer to that as a regression problem. So we have classification problems for categories, regression problems for categories. Now, I'm going through all of this because it's important for you to understand that before you continue. Otherwise, you might be not sure what's happening, depending on how much you have learned before doing this course. So it's just to ensure that everyone is at par of when it comes to understanding just basic concepts in machine learning. So at the very basic level, when you're creating a machine learning model, you would tend to use what are called algorithms to create machine learning models. Now, you could decide to create one or two or three or four, or just one machine learning model using just a common machine learning algorithm, such as KNN or decision trees. But you might get to a point where the machine learning model that you've created does not perform as you would want. It does not meet the metric of success in your case. So what do you do in such a situation? You could decide to go back to the data, ensure that you get more data in order to train that machine learning model to perform really well. And if you try to do that and perform those techniques, they usually call feature engineering techniques, you might realize, oh, actually the machine learning model still doesn't perform as we want. So what do? You can resort to using multiple machine learning models at the same time. And this is where ensemble learning comes into, because it means that it's an advanced way of saying, okay, let's combine multiple techniques together in order to make some sorts of predictions. So ensemble learning just refers to that process of using multiple predictive models to solve for those classifications or regression problems. Now, and the goal usually is to improve the accuracy of results by those models, which reduces what is called bias and variance. When you reduce bias and variance, technically, you're actually improving the accuracy of your machine learning model. And some good applications would be of usage of such models, where you combine multiple predictive models, would be in health, in manufacturing, and in also some other cases we'll also get to learn more about. There's some fundamental concepts that are important when you're using ensemble learning methods. There's max voting or majority voting, and this refers to the process of using yes, it's usually more of when you're using multiple ensemble on multiple models, so multiple machine learning models to make a prediction. You could decide, in the case of classification, to look at how most of the machine learning models performed, and decide to use the approach of, if a majority of the machine learning models corrected decided to predict one way, maybe they decided to predict that this new record should be a yes, then you would opt to use what is called majority voting and decide to stick towards that. You say, okay, maybe 3 out of the 4 models that we used in our case in this situation actually predicted that our outcome is a yes, so we are going to stick to a yes. That's usually called majority voting, because only one predicted wrongly. Only one predicted otherwise, which is not, which is not what you want. But generally, the idea here is to ensure that you have a fairly better accuracy that than just using just one particular model. There's averaging, so this comes into play when you're doing regression tasks. The first one was So assuming it was more relevant to classification problems where you are predicting a class, yes or no, and you realize three of them predict a yes, and then you stick to yes. So that's the concept that you'll be using there, is majority voting. But when you are you're trying to predict some sort of numerical value, in the case of regression, then you would use you would tend to apply averaging, which just involves using an average of what each and every model predicted, as using the average of all the results for that as now the result of what you would want. There's weighted average, which is just another concept of putting some more emphasis on certain models instead of just using just instead of just having all of them equally weighed on the final outcome. So you could decide to add some weight on some of the models. There's overfitting. This is where this is a concept where a model tends to perform badly as a result of just learning so much from the data that it was trained on. So overfitting, and machine learning models such as decision trees tend to fall into this category, which they just machine learning models based off that algorithm tend to fall towards this category. Yes, they perform well, but they forget that they learn so much from the data such that when you give them new data, they misclassify that data that doesn't really look so much from what it learned from. There's underfitting. This is where a machine learning model is too simple for it to be able to make predictions. So it keeps on making incorrect predictions because of the fact of underfitting. Those are just some fundamental concepts that will come into play. Now, what you're seeing on your screen is just a basic data science process when it comes to working on data science projects, especially ones that concern the creation of machine learning models. So we normally start off with, first of all, understanding the business question or the research question, and then setting our metric of success. Then we move on to data understanding, which just involves being able to pull the data and also read the data that you have, understand it, try to explore it to understand whether maybe possibly you have a fairly balanced data set, etc. And just understand what data you're working with, and is it suitable for you to use it for some certain models over others, because certain ones have some certain assumptions, etc. Then once you do that, you get and you do data preparation. It could be that there are outliers, there are missing values. So that part of even understanding, you now apply, you now respond to making modifications. You might decide to manipulate your data so that it doesn't have outliers, because that would affect how a model or machine learning model would make a prediction. Then you'd perform data modeling, which just involves splitting a data set into what is called a test data set and a training data set. A training data set would be that data set, and those data sets would actually originate from the original data set that you have. So you would split that original data set into training and test data set, and the test data set would be used for training the machine learning model so that it learns how to make predictions. And the test data set, you would use it to test whether the model performed correctly or it did not. So you just use the test data set for checking the performance of your model. In certain instances, you might also want to perform what is called hyperparameter tuning, which is just ensuring that you use the settings, they usually called parameters, for each model. So each model usually has, depending on whatever algorithm that you use, has different settings, or they're called parameters or hyperparameters. And you would normally find the best combination of hyperparameters that would work best for that. And in such a situation, we normally split actually the entire data set into three. A training data set, that's the biggest one, then could be 70%, then 20% of that original data set you have is the test data set, and 10% is the validation data set. So, but that happens if you really want to do that. So we split the data set, we build the classifier using now the training data set, we evaluate using the test data set, and optimize the model using the validation data set. Then later we can deploy the model and present it to users or various stakeholders. On the right, or what you see is just an image of what is called the CRISP DM. It's a methodology that's quite popular when it comes to data or machine learning related projects. So you could always have a look at that. It's called CRISP DM. So just to get into different categories of ensemble learning techniques. So there are sequential techniques, there are parallel techniques, sequential and also stacking techniques, which just involve using sequential as well as parallel techniques. Our focus for this workshop will be on sequential and parallel. There's a whole lot to cover when it comes to ensemble learning techniques that could also be covered in a further workshop or further course with regards to ensemble learning. So ensemble learning techniques normally involves sequential techniques, which generally these are types of ensemble learning techniques that the approach that would use an approach that's similar to a sequence. So you could have, let's say, 5 different machine learning models, which of course you want to use all of them together using in an ensemble manner. So the idea here is to first of all use one particular machine learning model, the first one, make some predictions based off a training data set that you have, and then of course you will assess its performance, but it usually happens behind the hood. Once you have gotten to understand how it performs, then you make now predictions. You also now train the second model and make predictions. But when you are training your second model, you take into account the performance of the first model, and you do that for each and every of the 5 models. So the model 1 will take into account, actually model 2 will take into account the shortcomings of model 1, and model 3 will take into account the shortcomings of model 2. Model 4 will take into account the shortcomings of model 3. The same case, and model 5 will also take into account the shortcomings of model 4. So ideally, what you have here is a process where models tend to learn from each other, and they try as much as they can when they are being trained to ensure that they make the correct predictions that were that resulted in errors in the previous performance of the previous model. So normally these types of techniques which we would use in this particular case, which are normally sequential, they usually use this sequential approach, are usually referred to as boosting techniques. So they tend to boost the performance of the previous models in that whole process. So that's usually the sequential approach or the sequential ensemble learning techniques. The parallel ones would be more like the parallel one would actually make predictions, but independently. So assuming still, again, you have those 5 different models that you're working with. It can be either KNN, decision trees models, or it could be SVM, etc. Whether it's regression or classification, but if it's regression, you have to use only regression models. Same case for classification. So if you have 5 of them, model 1, 2, 3, 4, 5, and you want to use their parallel approach when it comes to ensemble learning techniques, what would happen is that each and every model would be trained on some sort of sample from the original training data sets. So a sample from the training data set would be trained on model 1. A sample from the original training data set would be trained on model 2, etc., etc., etc. And the idea here is that once you have individual results, you could perform what is called majority voting, if it's in the case for classification, because you're trying to predict a class. So you would go with the majority, the most popular predicted class. Or if it's in the case of regression, you would do some averaging of all of the some average of the results that you will have gotten. Yeah, and that's generally it. Sequential and parallel, that's normally what you would do. Just to get into some details, I've already even mentioned what happens. I think when you go to sequential techniques, which are boosting techniques. There are various ones. There's Ada Boost. There is Gradient Boosting Machine. That's called GBM. There's XG Boost. There's Light GBM, and there's also Cat Boost. And these techniques, these algorithms, we can use them to create models that tend to boost other models in the process of training. And the idea is that they are able to make much more better decisions in that whole process. Yeah, so that's usually boosting techniques. I think I can even just go through a few more details, like Ada Boost, which is the first one, and maybe one Ada Boost, Gradient, that's GBM, and also XG Boost quickly. Ada Boost would actually conventionally apply that technique that we've mentioned, where you boost the previous model's performance. And the idea behind this particular use case is that you combine multiple weak learners. It could be decision trees, it could be KNN, it could be other learners, to create a strong classifier. The idea is to have a final ensemble learning technique that is as a result of these base models that don't perform well by themselves. And you would use AdaBoost because you want, of course, to improve accuracy, and you also want to overcome the shortcomings of individual machine learning models, such as is possibly naive Bayes or KNN or decision trees. GBM is another technique it's called gradient boosting machine that we can also use. Still also applies the same techniques as AdaBoost, only that in this situation you'd be more focused on decision trees and improving decision trees. You could also still perform classification and regression tasks. But how it works, you usually start, say, with an initial model, you calculate the residuals or the errors that it performs. Then subsequent models would be trained to predict those residuals and ensure that those errors are reduced over time during those subsequent models. And the final prediction is usually just the sum of all the predictions. And yeah, so and why would you use it? Again, high accuracy, and also if you have a data set that that doesn't have linear relationships. So inside, if you have the data set that the variables are not related to each other, then you can be able to do that. By related, I mean correlation. If you could use something like a scatter plot to determine whether there is a relationship between one particular variable or the other. And also, it's important to note that GBM also is quite robust to outliers. So if you have a data set that has a lot of outliers and you don't want to get rid of them, if they are genuine outliers, then GBM does a really, really good job of that. There's XGBoost, which is quite popular in machine learning competitions. Stands for extreme gradient boosting. It actually applies the same concepts as GBM, only that it's an extension of that, and it provides other functionalities, such as being able to use what are called regularization techniques to reduce overfitting. So it has that enhancement. It also uses what is called a customized loss function to be able to perform whether it's a regression task or classification task much more efficiently. It has an option for handling missing values, and you can also implement parallel or be able to use the memory that you have in a distributed way for faster training. So you're able to get the model that you are working with take less time when it comes to training. Why would you use XGBoost? I mentioned there it has several enhancements, which I've talked about that, and it allows you to get high accurate results. It's quite robust, and it also offers regularization. On the other hand, leaving alone now sequential techniques, moving on to bagging techniques, where You have weak learners, weak based machine learning models, and you just which you would, and the idea here is just to independently have them be able to perform their own predictions. You train them independently, perform their own predictions. In such a situation, you would be performing bagging techniques, and but bagging, you would not be perform. You actually be implementing the parallel approach. But when it comes to this approach, there are key there's one or two things that you need to take into account. One is bootstrapping. So whenever you are training a model, say when using this technique or using a bagging technique, you would need first of all to, yes, have a training data set, but you would get a sample. Let's say for one particular machine learning model, get a sample of that data and then train it, use that data to train one classifier or one regressor. The same case, another sample, then the other regressor or classifier, the same case with another one. And once you have done that, you can be able to either perform majority voting, or in the case of regression, averaging. You could do averaging and be able to come up with a result. So that is usually the approach that you would tend to use. And that process of sampling, we would normally refer to that as bootstrapping. And when we are aggregating, at the final end, in terms of our results, we would perform aggregation for the case of regression. Yeah, so generally there are of course some benefits and trade-offs. Here you of course are able to combine weak learners and have a strong learner to make some more some fairly accurate results. And in the process, you're also able to reduce overfitting. But the only problem also here is that bagging is quite it's computationally expensive, and sometimes it may not be desirable in some cases. A few techniques that we could use, I'll just go through two. There's a bagging meta estimator provided by sklearn that actually implements that process that we've mentioned here, where you have training data sets, you have bootstrapping happening, and then weighted, and then you have majority voting or even averaging happening at the very end. So there's the bagging meta estimator that implements that particular approach. Random forest is another technique, a bagging algorithm that we can use. And this algorithm combines multiple decision trees, just multiple decision trees, to create a robust and highly accurate model. Again, it still uses the same concept of where you have multiple, yes, decision trees, but they work independently. And then you come back again to perform majority voting or averaging for either whether it's classification or regression. The reason why you do this, you would actually end up reducing overfitting, which normally individual decision trees experience. And also, when while working with random forest, you can be able to handle a data set with outliers, as well as if you also have high dimensional data, you can also be able to handle that. Um, why? So generally, just to recap, why is ensemble learning important? You're able to get improved accuracy, so you combine multiple models, leading to more accurate predictions. Um, Secondly, enhanced generalization, so you're able to reduce overfitting, so you help models perform really well on new data. Thirdly, risk mitigation. So for organizations that are looking towards ensuring that they do not deal with the failures of using a single model or single machine learning algorithm model that's based on just an algorithm. So risk mitigation in this case is that you're able to deal with the effects of just using just one machine learning model. So instead, you now decide to use multiple, which you're able to mitigate those risks when it comes to machine learning. So when do you apply ensemble learning? It's not every time you do that. In most cases, the first thing that you do, you create your machine learning model using the base or the basic machine learning models that you're used to, whether KNN, decision trees, logistic regression. In the case of classification, in the case of regression, use linear regression. Um, First of all, you create those ones, and when you realize you haven't really gotten to have met your metric of success, or you also want to ensure that you are prone, you have some model proof solution, then you can opt to think about ensemble learning. So where there are high stakes and critical decisions with regards to machine learning models, then you can be able to do that. Again, when you also want to ensure that your model, the single models that you're using, and if they are not showing any significant improvement, and you've also probably gotten to their performance limits after performing optimization techniques such as getting more data, engineering the features or independent variables, and you realize you're not getting more performance, then you can opt towards that. And when don't you not use ensemble learning techniques? That's usually um, when you're looking at maybe when you are looking at explainability. So some of these models can be quite hard to explain. They can be black boxes. So you might decide to just use one machine learning model in such a use case, or even when you don't have lots of resources at your disposal. So sometimes you just want to use a machine learning model that works, or even when you also have just a base model that just works, you may not need to go this further. All right, so at this particular point, you can pause the video and you can continue to the next section, which just generally will involve going through the reading that we had curated. So this is the reading. Go through it for 10 to 15 minutes to just reinforce what we have covered so far. And once you have done that, go through this quiz that we've also provided. It's a self-graded quiz that should give you a good understanding of those concepts that we have had. The idea is just to have a firm understanding of the fundamentals of ensemble learning before we now go into application of those concepts. So do that and then come back once you're done. All right, so the next thing that we're going to do is to go through the practice work. So we've shared the link to this notebook already. So open that up and you should get to this page. Once you get to this page, this is a notebook that we can use to learn or to put into practice those ensemble learning techniques that we have learned. The first thing that you need to do is to go to File, then save a copy in Drive. So File, then save a copy in Drive. That's what you need to do in order to make a copy of this notebook that you can use and edit and also save for your learning. So once you do that, you should see a new tab with the same copy open up. You can rename that copy, the name, and then once you do that, the next thing that we will need to do, so you can even pause the video if you want, and then the next thing that we need to do after that, once you have done that, is to connect this notebook to Google servers. So this notebook would be hosted, the one that you've created would be hosted on Google Drive, and Google provides an application called Google Colab to be able to work with the notebook. So on the web, that's from actually Google Drive. But now in order to run the code that's within the notebook, we need to connect the notebook to Google servers. And you need to go to the far right. When you see connect, just click on that and our notebook should be connected to Google servers once it says connected, and you'll see a green check that will show up there. So just do that. You can depends. Sometimes it takes less time. Sometimes it can take um, you know just more time. But it has done that. Once that is done, we now need to go to the next section. So once you have connected it, you need to go to this section. So we are going to, the other thing that we're going to need to do is to import libraries that we will use for ensemble learning. So libraries are just a collection of code that we can use for just performing specific tasks. For example, we have pandas for data manipulation tasks, matplotlib for visualization, sklearn for machine learning tasks, and that's what we're going to use for this workshop as well. So let's just import those two. Let's import first of all just some important libraries that we'll use. If you see this pop up, don't you need to save a copy in Drive, but if you don't see it, it's okay. I'll just run anyway because I don't want to make any changes to this document. We'll import these two libraries, that's pandas as PD for data manipulation and NumPy for scientific computations, just for perform any sort of conversions that we might want. Or perform even some data manipulation tasks as well. It also has that ability to do that, such as selection. Let's import these ones first. We'll import sklearn later when we need to. So going through now examples, we have classification and regression examples. In classification, we'll get to work with Ensemble learning techniques for classification, and also in regression, we'll get to learn more about regression techniques for that pertains to Ensemble learning. So let's first of all see what we have. We have this question: will John, 40 years old with salary to 2,500, buy a car? Will he buy a car? Based on this data set, we're going to import our data, then prepare it, perform data modeling, and then in this case, we're going to answer this question that we have. So let's first of all import this data set, which we will do, and load it in this variable, sociodf. Once we do that, we'll call this sociodf a data frame. So we can also be able to preview the first 20 or a sample of 10 records, a random sample of 10 records from this data set to understand how the data set looks like. So we can do that. So this is how the data set looks like. We can preview the size of the data set by checking the columns and the records and columns. So this is 400 records and 5 columns. Okay, moving on to prepare our data set. So in our case here, we're going to just prepare a data set. So you see this, the variables that we're really interested in for independent variables, we will not work with this variable. We'll only work with gender, age, and estimated salary as the predictor of features or independent variables, and the variable of interest or the label target will be purchased. So first of all, we need to perform some conversion. We need to perform some data manipulation on this gender library so that we have numerical values. Many machine learning models don't usually take in textual data. There are, such as one that is called cat boost, categorical data, but now for this one, for most of them, they don't. So we'll update male. For male values, we'll update that to have 1, and for female to have 0. So let's do that in the next step over here. So we refer to the column that we want to perform the conversion to. We use NumPy to perform that operation on this other side, and we use the where function. We want to check the gender column, and if that column contains male, and replace it with 1, and female, replace it with 0. That's what we do. And we can preview that by using sociodf.head to be able to see that change that we have made. So for gender, you have 1 and 0s. So once we have done that, we now need to go to the next step, where is, yes, we have now a data set that looks okay. It's prepared, but we need to drop this. We only need to select the independent variables and the target variable, that's a dependent variable. So how we do that, we can use the iloc method and apply it on the data frame that we have. So sociodf, we use the iloc method, we select all the records that we have. The second bit that we define is the actual columns that we need for this case. So we want age, gender, age, and estimated salary. And we use the positional indexing approach, where each column has an index, so our position. So this is the user ID column is position 0, 1, 2, and 3. So gender is 1, age is 2, estimated salary is 3. That's why we define those positions here to be able to retrieve now the columns, and we get the values for those columns and using .values property, and then we store that in this x variable, which will have now the independent variable values. Same case we do for y, but now for y we only want just one column, which is purchased at position 4, and we save that in y. The next thing, so let me run that. The next thing that we need to do is to split our data set into a training data set and a test data set. And we can do that using what is called a train test split function. So rather than writing code to split that data set from scratch, we can import this function from sklearn.model selection. And then in the next line, we define 4 variables. The first variable will contain independent variables. That's the future, or that's the feature variables in the training data set. The xtest variable will contain the it will contain the independent variables for the test data set. Ytrain will contain the independent variables, not the independent, the dependent variable for the train test, and the dependent ytest will contain the dependent variable for the test data set. So the values will be stored there. So we use train test split, and it will create 4 different data sets, and all those will be stored within the respective variable. But again, this function takes usually the following arguments. There's x, which is now the independent variables, y, the dependent variable values. We also specify how big we want the test size. We say 0.25 to define that we want 25% of the entire data set to be a training data set, to be a test data set, and then random state to ensure that we have a reproducible data sets. We have these data sets can be reproduced by anyone else. If we don't state this, every time someone runs this, we'll always get a different value. And sometimes you can, as long as you set it, it could be 0, any just value, 42, 1, 23, it will work. But most of the times, usually 0 or 42. In many texts, you'll find that. So run that. That should be good. The next thing that we do is to perform what is called feature scaling. So in our tests, in our data set here, you'll see that there's some values which have large numbers, and this might affect how the models perform. So in order to ensure that all values, this aspect of having large values isn't a determinant in how our model performs, we can have all these values within the same range, or the feature values within the same range of 0 to 1. And that's what we do here. That's what we use. We perform what is called normalization to scale our data between 0 and 1, so that we are able to take into account of that factor. So, and we do that for the independent variables x train and y tests, which you see here. Do that. Once we have done that, the next thing that we need to do is actually now create our models, our machine learning models. You'll note that the reason why we are going to, so the next thing that we're going to do, we are going actually to create machine learning models individually, how they perform individually. This is what we're going to do. And then how they also we're going to also do the same thing for how, what, also we're also going to implement ensemble classifiers or ensemble machine learning models. So we have base models and now ensemble models. In our case, we are performing a classification task. So we use we use now classifiers for this case. On the other side, we could use regressors. Even logistic regression is usually a classification algorithm. For an equivalent for regression for this usually is a linear regression, which but they all work differently. They're not equivalent, by the way, they work differently. Only that logistic regression is only for classification, and linear regression is for regression. So we import those different algorithms or classes, if you go the Python way. We also import XGBoost, which usually comes in as a library. You can even have a whole lot about XGBoost that you want to learn. Once you have done that, we have imported these algorithms. We then create the models that we want for the base models. And also we do that for the ensemble models. Then once we do that, we now train all the models together. So we will train the base models using the train data set, the train independent variables, and the again train, that's the dependent variable target values. So we do that for the base models as well as for the ensemble models. And we also have identified these are the bagging classifiers, these are boosting classifiers. So yeah, so let's run that. This may take a bit of some time, maybe a few seconds, and it has actually trained really fast. Once we have done that, we can now make predictions on how we can make predictions for the test set. So when you're using the test data set, we normally, in order to assess the performance of models, we would set aside the original values for the target variable of the x for the test set. We set it aside. Those values, we set them aside. Then we make predictions using the independent variables for the test set. So we are trying to make predictions for the y test. Now we make new predictions for y test. And then we compare the predictions of the models versus the original values to see how well they were able to have performed. So that's what we are doing here. We're just making predictions using the X test dataset, the independent variables of the test dataset, with all now the classifiers, including the base models as well as the not the base models but the ensemble models. And we've done that, and then we now check the accuracy scores, and we import our classification a classification report, which we'll use later in the next step, and accuracy score. So we want to also use to check the performance of all models and compare them. Well, the expectation is that we want ensemble learning models performing better than the base ones. So, and here we go. So we have these models which I've highlighted as the base ones, the base models, and these other ones as the ensemble models. And you can see, okay, so quite a number of the ensemble ones. Actually, there are more ensemble that had over 91. Actually, the least one had 90, 0.9. So it means 90% of its predictions it made correctly. Maybe 10% are the ones that it made poorly. But generally, this gives you an idea. Sometimes you might realize something like this doesn't make any big difference if you are to use just the tree, or even just a KNN over maybe even actually KNN outperforms all of them. So you might even resort to just using KNN in many situations, or even some situations you might realize SVN, not SVN, it's supposed to be SVC, or SVM, M, not M. Does actually a good job of that. Just checking something. Okay. All right. So I think once you have understood this, but you can still further create classification reports for that, for you to just have a good understanding of how the models perform. Like if you want to check the precision recall metrics, F1 score. These are just other metrics that we can use to understand how they perform. But the one that I would recommend mostly would be just using what is called a confusion matrix to just check the true positive, true negative, false negative, and false positive values for that, because that would give you a good idea of what would happen. But yeah, but generally we can decide to use those models to just also make our predictions. So for that prediction that we had, so the case was predict whether 60 years with salary 2,500 would be able to buy a car or not. So one would represent a male, so that's John, 60, then 2,500. This is the new data, and we transform it, and then we pass it to our models. Then let's run that and see how they all predict. They've all predicted the same, that all that John will actually buy a car. And yeah, so that means you can be able to use that as a new prediction. You can even use these models to just make new predictions based on that data set. But this is not a real life data set. The data set that we used here was just a hypothetical one for learning, but you would expect to have quite a large number of features. So you would need to figure out a way of just pulling those features and ensuring that, and also cleaning new values, new features for the cases that you want to predict. And that's it with regards how to you implement classifiers. And this is just a basic way, but you could still go deeper into understanding how each and every parameter for or settings for each and every bagging or boosting classifier works. But the idea here was just to learn how to implement ensemble learning techniques for classification. Now, moving on to regression. So this is, we've covered now classification. Now let's move on to predicting some sort of value. So create a decision tree model. Well, actually this shouldn't be a decision tree model, but it should be create a decision, create a model using the following dataset, an ensemble model. So we'll use this dataset. So let's load it. And we want to predict, so usually we want to predict the weight. Sorry, I did not make that clear. And the idea is to predict the weight. This is usually um, the variable of interest for our use case. So we can check on whether we have any missing values, 159. These are okay. It's a clean data set, and we could always just do that. Our focus is not cleaning and performing exploratory data analysis. Our focus is just generally on machine learning and ensemble learning. So let's split our data set. We use a different method of selecting the different values in our independent variables. So these are the independent variables: length 1, length 2, length 3, height, and width. Um, so these are the independent variables, and this is the dependent variable. So we save that in X, the independent, and dependent in Y. We create the variables that we have, and then um, um, we we split our data sets, but here we want our test size to be 30. Sometimes you can just play around with this number, maybe 25, 20, to just get one that gives you the best outcome possible. So, and also we put a random state there. So run that. We now create our regressors. In our case here, we are working with just regressors. And here we are importing just the normal regressors. We just decided for this case to just create one base model. We won't create those other ones. I think you could always do that if you want to compare the performance. But we also have our our um, our ensemble learning techniques. And for XGBoost, we normally need to describe the objective function, which is regress squared error, which will help us determine how our model performed. We will normally need to specify at the very beginning. Then we train our models by fitting our data to the regressors. Just means training. So just click on that. The reason why we are getting this output, it's because this was the last model to be trained. Then we make predictions. So on the X test. And then we can actually even check the predicted values for what was there. So we can do that in our use case, but here we would be doing this because of the decision regressor is what we would be comparing that with. So for decision trees, we would see that this is what it was able to predict, the one on the right hand side, and the actual ones were this, but you can see they mix quite a large number of mistakes. So if we check for regressor for random forest, 390 for 32, actually okay, I'm not sure, but it made quite a large number of mistakes. We can check that for adder boost. You can check for adder boost for 12 closely. It's moving towards 390. Adder boost was a bit better. For GBM, it actually did a bit worse for the start record. What about for XG boost? We may not be sure, but again, this is not a good way of just well, just observing the records just gives you an idea that yes, it was able to make errors, but you may not be able to. It's not until you do the math to see how well the model performed or not. So this is just to give us an idea, but we can now get the RMSE, that's the root mean square error, which is the metric that we normally use for um, regression. And we can do that, we can calculate that for all the machine learning models that we've created, that's the regressors. And the one that's closest to zero usually refers to that it's a better model. It just implies that's a better model. And there you have it. So we have 188 decision trees, 161 bugging estimator, random forest 163, but 140. So XGBoost actually performs better than all the others. And in order to even make this a whole lot better, you can still continue performing optimization techniques such as getting more data, um, when it comes to maybe columns of data, even when it also comes to the number of records that you have. Could even just also mean tweaking the configuration, the hyperparameters for the actual machine learning model that we're working with, etc. But I hope that gives you just a good idea of how to implement ensemble learning techniques for both regression and classification tasks. Now, the next thing that you need to do is to work on those two challenges. There will be one for classification, another one for regression. And once you have done that, just verify your challenges with what we have here. Once you have done that, and we've tried as much as we can to have a good data set that just allows you to perform, to apply what you have learned. Once you have done that, the next thing would be to go through this project, which will help you to put into practice what you have learned so far. We have also provided a guiding notebook that will just give you an idea of how you can be able to apply the project, to apply and the techniques that you have learned in a real life project. Then once you do that, you can just verify your solution with the solution notebook that we have provided. And yeah, so that would be it. That would be what you can be able to cover so far. I hope this learning experience takes you through a learning journey that just helps you to spend the most in learning whatever that you need. And in terms of next steps, where do you go from here? Possibly you have, if this is your first course, I would highly advise that you brush up a whole lot of other skills that allow you to work on such projects. You can look into regression or classification analysis courses that we have. There's also statistical data analysis course that just helps you to apply some of the exploratory data analysis concepts. If you're also not really sure, not comfortable with regards to even analyzing data, you could look into a data analysis or even data wrangling course for data cleaning or preparation. If you're really, really, really green, look into working with introduction to go into the course entitled Introduction to Python. But if you want now to move on to the next thing, you could now decide to go to learn a bit more about what is called unsupervised learning. So learning about clustering analysis with Python. That's a course that we would highly recommend. And yeah, so that's it. If you have any questions, feel free to ask in the comment section or description section of whatever platform that you're watching this particular course from, and we'll be more than happy to help you out. And all the best in your learning journey, and see you in the next course that you would want to undertake in relation to data.